Welcome to the lecture on imaging and deconvolution for the 2021 SMA school. I'm David Wilner from the Center for Astrophysics, Harvard and Smithsonian in Cambridge, Mass. So in previous lectures, you followed the signal from the astronomical source through the atmosphere to the antennas, to the correlator. You've performed calibrations, and now it's finally time to make an image. So my goal in this talk is to give you some intuition about interferometric imaging. I won't be 100% rigorous at all times. I'll try to avoid equations for the most part that you can read about in the references that I'll show you in a moment. But I hope you'll leave this talk with a better understanding of the imaging process, as well as the need for deconvolution and what that involves. So here's a list of the topics that I'll cover. I'll very intentionally review some of the topics that you've heard about already in previous lectures. I'm going to discuss Fourier fundamentals, go over aperture synthesis and UV plane sampling, then go on to imaging specific topics like the fast Fourier transform and gridding, visibility weighting schemes, deconvolution, the clean algorithm and maximum entropy algorithm, and then a few miscellaneous topics at the end, which you may find useful. So first, here's a list of references that are very useful. Thompson, Moran, and Swenson, the textbook, this is the Bible for interferometry and synthesis imaging and radio astronomy, and really the ultimate reference. If you need an equation or a lengthy discussion of some topic, I expect it's in there. Another useful resource are the NRAO synthesis workshop proceedings. These have excellent chapters and lectures on imaging and deconvolution. Another fantastic and somewhat hidden reference is the proceedings from the IRAM interferometry school, in particular the chapters by Stefan Guillotot. There's the essential radio astronomy course online, and many other great talks on the web from ALMA, from Australia, from other schools that provide really nice pedagogical presentations that maybe come from a slightly different perspective than this one and can help inform your understanding. And last, I'll mention the Event Horizon Telescope paper on imaging the M87 black hole that explains very clearly many of the important concepts that we'll discuss in this lecture. All right, so we're going to start with the Fourier transform. The Fourier transform was the subject of one of the first XKCD cartoons, which is one statement about how important this is. But if you're going to do radio interferometry, it's really helpful to know the fundamentals of Fourier theory and some basic properties of the Fourier transform. So starting with Fourier fundamentals, what Fourier theory states is that any well-behaved signal can be represented as the sum of sinusoids. And the classic example of this in the textbooks is the square wave. The square wave is not an especially sinusoidal function, but there's an infinite series of sine waves that can represent that function. And the Fourier transform is just the mathematical tool that decomposes the signal into its sinusoidal components. And the important fact is that the Fourier transform of the signal contains all of the information of the original signal. And since this concept was developed by Fourier centuries ago, a lot of applied math has been built up around it, and that's useful for radio astronomy to take advantage of. So I think it's really useful to acquire some comfort with the Fourier domain. And I particularly enjoy this quote from Bracewell's classic text that functions and their Fourier transforms occupy upper and lower domains as if functions circulated at ground level and their transforms in the underworld. And you can decide whether it's the images or the visibilities that are at ground level or in the underworld. Okay, So let's go over a few properties of the Fourier transform. The notation I'm using is shown here. There's a small g of x is the function, and its Fourier transform is the capital G of s, where x and s are Fourier pairs of coordinates. So addition in one domain is an addition in the other. So if you add two functions, it's the same as if you add their Fourier transforms. Multiplication in one domain is a convolution in the other domain. So that comes in handy. There's also a scaling relation. So something that's large in one domain is small in the other domain. And an offset in one domain is just a phase shift in the other domain. So these are useful properties that come up often and are good to know. So now let's return to the radio interferometry application. Here's the key equation that I'm assuming that you've seen. And the visibility function, this capital V of U and V, is the 2D Fourier transform of the sky brightness distribution, which I'm calling T of Lm here, under certain conditions that you can read about that essentially almost always apply to the SMA. That is, the source is incoherent, the field of view is small, the source is in the far field, et cetera, et cetera. These can be relaxed in radio interferometry, but then you do have to be careful about what this means for this simple Fourier relationship. So I said the brightness distribution, we're going to call throughout this lecture T of Lm, where L and M are angles in the sky, typically measured in radians. And the visibility is then a function of U and V, where U and V are spatial frequencies that are the Fourier pairs of these angles, and they're typically measured in wavelengths. So a short baseline with small U and V gives a wide fringe pattern and low angular resolution, and flux from extended sources add up, and you typically get a high visibility. By contrast, if you have a long baseline with large U and V, that gives you a narrow fringe pattern and high angular resolution, and flux from extended sources average out, and you get a low visibility. So I'll show this in a schematic form in a moment. A couple other things, if you put 0, 0 in for U and V, so you're at the origin of the UV plane, which, by the way, you can't get to with an interferometer because you can only get the antennas so close together. If you do put in 0, 0 in this equation, you get the integral of the brightness distribution over the sky. In other words, you just get the total flux density of the source. And sometimes we call this the zero spacing value. Another property is that the sky brightness is always a real quantity. So if you make a measurement at minus U minus V, then you get the same value as the complex conjugate of the visibility at U and V. So that's useful because if you make one measurement, say at U and V, then you also get the value at minus U and V. So you get two visibilities when you make one measurement. So now I'd like to try to visualize these visibilities. As I mentioned, they're complex quantities. There's nothing complicated about that, but they can be expressed as either real and imaginary parts or as amplitude and phase, depending on what's most convenient in the context. All right. So here's an image of the sky. It's a brightness or intensity distribution, right, that I'm calling T of Lm, where L and M are the angles on the sky. Some of you may recognize this brightness distribution is, in fact, Rick Perley, who gives the introductory lectures on interferometry at the NRAO summer schools. So here's his Fourier transform. It's the amplitude and the phase from this particular image of Rick. And you can see there are features in the amplitude that are reminiscent of features in the image. And the phase is more scrambled. But the point I want to make with this is that if you just pick one value of u and v, there's the amplitude and phase of a sine wave with a particular period that contributes to the image of Rick through the Fourier transform. So every point in the UV plane provides information that is somehow everywhere within the image. Also note that since Rick is real, the pattern that you can see in the amplitude is symmetric. That is, u plus u and plus v and minus u and minus v have a symmetry. And you also see that there's a peak in the center, and that's Rick's total flux density. So there are a few good, few simple Fourier pairs that are really useful to have at your fingertips. Oh, there's my point that each v of uv contains information everywhere in the image. But there are a few simple Fourier pairs that are good to know at your fingertips that I'll illustrate next. Okay, one is a delta function. So a delta function is a point. It's the skinniest function you can make. It has infinitesimal extent. And its Fourier transform is a constant. That is, it's the broadest function you can make. Another one is a Gaussian function. The Fourier transform of a Gaussian is a Gaussian. So that's easy to remember and very convenient. If you have an elliptical Gaussian, that is, it's a two-dimensional Gaussian, its Fourier transform is also an elliptical Gaussian. But you can see in the picture that the skinny part gets fat and the fat part gets skinny. And that's a direct consequence of the scaling relation that we mentioned earlier. So one thing to remember about Fourier transforms is that narrow features transform into to wide features and vice versa. Here's one more example, a uniform disk. The Fourier transform of the disk is a Bessel function. And the Bessel function has lots of ringing in the UV plane. So anything that has sharp edges in one domain, like this disk here, or the square wave that we saw earlier, will have a lot of oscillations in the other domain because you need a lot of narrow sine waves or high spatial frequency components with different phases to represent the sharp edges. Right? Anything sharp in one domain generally oscillates in the other. So what does all this mean for radio interferometry? So here's this equation again. We have our brightness distribution on the sky, T of Lm. We have this, argument inside the integral, which is e to the 2 pi with u and v and L and m in it, and an I, and then we integrate over this. So all this exponential term is a bunch of sine waves and cosine waves that are multiplied by the sky brightness within the integral. So let's imagine that we have a compact source that we see here on the left side. It's a little compact brightness distribution on the sky. You can see it has some fine scale structure, and it's a happy source. So here's our short baseline interferometer. This is two SMA antennas close together, and they make a wide fringe pattern. So this grayscale is supposed to represent the fringe pattern on the sky, where white is positive and black is negative. So what does this equation say? The equation just says you take the sky brightness, okay, that's our source. We multiply it by this fringe pattern, which is just this sine wave. And then you add it up inside the integral. That's what an integral is. And you get a number. And that's the visibility of the source. And so because it's a small source here, which falls inside the big broad fringe, you get all the flux of the source in that number. Okay, now let's suppose we have a longer baseline. Okay, so same source. but antennas are now farther apart. We have a long baseline. So this gives us a narrow fringe pattern. So the source is still small compared to the fringes. So when you do this multiplication in the integral of the brightness distribution times the fringe pattern, and then you add it all up, you get a number. And that number is the same number as we got before with the wider fringe pattern. So what's that telling you? That's telling you that the source is small. What's the Fourier transform of a delta function? It's a constant. That is, the visibility is the same for all baselines. And that's the exact situation we have here, right? We measure at different baselines, we're getting the same number. That's telling you that the Fourier transform is a constant and the source is small compared to the fringe pattern. And if we rotate the fringe pattern, we get the same story. If we do the multiplication and the integral, we get a number, and it's yet the same number. So all of this is telling you have a source that's smaller than the fringes. That is to say, it's not resolved by the interferometer. All right. So what happens if you have a bigger source? So this is a more extended source. It has some small scale structure on it. It's also a happy source. So if you have your short baseline with a broad fringe pattern, and you do your multiplication and summation for the integral, now you have some negative parts and some positive parts, and you get a number, and this number is going to be less than the total flux density of the source. And it's also going to be a bigger number because the source is big and the fringe pattern on the source is mostly positive. But now if we go to a longer baseline, the antennas are farther apart, and we have a narrow fringe pattern. This has lots of positives and negatives over the source when you multiply and add. So you're going to get a small number. That is, you're going to get a low visibility, which is telling you that you've resolved the source. It's a different number than the short baseline, a smaller number. And if you take a similarly long baseline, but at a different orientation, then you have another narrow fringe pattern, and you get a small number again. But it's going to be a little bit different small number than the last small number because of the small scale structure in the form of the happy face that's going to respond to this narrow fringe pattern. So the whole idea of interferometry is to get enough numbers like this to reconstruct what the brightness distribution on the sky looks like. So if you understand that basic principle, which just goes back to this basic equation, then you're in great shape. Okay, so in a little more detail, the basic idea is to sample the visibility function, V of UV, at enough UV points using distributed small apertures to synthesize a large aperture. So for the SMA, this is 6-meter telescopes distributed over the plane on the summit of Mauna Kea up to 0.5 kilometer. So how do we do this? Well, if you have one pair of antennas, then you have one baseline and you measure 2 UV samples. Remember, that's because the sky brightness is real. So if you have n antennas, that gives you n times n minus 1 samples at one time. All right, well, you can only build so many antennas. So what can you do then if you want more samples? Well, then you can reconfigure the physical layout of the antennas to get different baselines and to get different samples. That is, as long as your source doesn't change in the time it's taking you to move the antennas around. So another way you can get more samples is to use the fact that the Earth is rotating. So your baselines are changing as seen from the source. In fact, it's hard to avoid the fact that the Earth is rotating. And so the baseline lengths and orientations change with time depending on the geometry of where the observatory is on the Earth and where the source is on the sky. And this was all part of the basis of Martin Ryle's Nobel Prize in Physics in 1974. So yet another sort of slightly more subtle way of getting more samples is to use more wavelengths. Because remember, the baselines, U and V, are measured in wavelengths. And this process is called multi-frequency synthesis. So this is useful if the structure is very similar over a range of wavelengths. Typically, this might be a continuum emission process with a simple behavior like a power law. This is not useful for something which changes with wavelength, such as a narrow spectral line. So here are essentially all of the world's general purpose aperture synthesis telescopes for observations at wavelengths that are shorter than a few millimeters. There's the giant ALMA telescope in Chile with its 66 antennas. There's the SMA on Mauna Kea with its 8 6-meter antennas. And there's the Iriam Noema in the French Alps, which will shortly have 12 15-meter antennas. So now here's going to be a real-life example of UV plane sampling with the SMA. So on the left side here is a topographical map of the SMA site on Mauna Kea. And each of the little numbered spots is a station where we can place one of the SMA antennas. So in this example, which is from a particular date in 2009, the antennas were on the stations shown in a compact configuration. So there were 7 antennas of the 8, with one of them inside the hangar undergoing maintenance. And the observations were at a frequency of 345 gigahertz, and the source we were observing is at a declination of 22 degrees. So remember, the UV samples depend on the location of the observatory on Earth, where the source is in the sky, when you observe it, and at what wavelengths. All right. So here's what happens with 2 of the antennas and 1 sample lasting 30 seconds. This gives us 2 points in the UV plane. So the plot on the left is the UV plane, U and V, measured in thousands of wavelengths. And on the right, I'm showing the Fourier transform if we assume a constant amplitude of 1 for the measurement at each point. So this is equivalent to the fringe pattern for the 1 baseline. And here are some labels to help you see a little bit better what's going on. We have a measurement at U and V, which also means we have a measurement at -U and -V. And that gives you a very particular fringe pattern, which shows up in the Fourier transform of the UV points. And now we can add another antenna, 3 antennas. Now we have 6 points, 6 UV samples, and there's a more complicated pattern on the right, because now we have a bunch of sinusoids that all interact. And if we add another antenna, then we get more samples, and another antenna, we get more samples, and another antenna, even more, and another, even more. Now we have 7 antennas. We've run out of antennas. So how do we get more samples? Well, we let the Earth rotate. So here's what happens. We let the Earth rotate for a little while, and for an hour, and for 3 hours. And now here's 7 hours. And this is effectively what we call a full track from the source rising to setting. And now our Fourier transform is starting to look a little bit like our delta function, with some extra scruff around it that comes because we just have a finite number of samples. But this is a real sampling pattern. There are missing bits in the UV tracks as the array is looking at calibrators. There are times when one antenna or another drops out because of a problem. And that's the reality of samples in the UV plane. If we were doing a multi-frequency synthesis for continuum emission with the SMA's swarm correlator, we could cover 44 gigahertz of bandwidth. Then for each sample, instead of having 1 little point in the UV plane, we have many points for each of the different wavelengths that we're observing. And the UV samples end up being spread radially, and the UV coverage is filled in more and better. Okay, so let me return now to that previous plot, the SMA compact configuration. I just replotted the UV coverage on a different scale. You see where the antennas were. And now we're going to do another observation with the antennas on different stations. This is the extended configuration with 7 antennas that were available, and the UV coverage looks like the following. So the baselines are longer, so it extends out farther in the UV plane. And now here's the SMA in the very extended configuration with antennas as far out as they can go on the Mauna Kea site. And here's the UV coverage from that. And we can combine these 3 observations together. And these points in the UV plane represent, where we've sampled the visibility function. So again, this is limited by the characteristics of the array, how many antennas, when we observed, how long, and the Earth sky geometry, as well as calibrations and equipment breaking and whatnot. That all gives these gaps and irregular sampling. But we can abstract this in the following way. There's kind of an outer boundary in the UV plane, and beyond this we have no samples. So there's no information from scales smaller than we've measured. So these sort of outermost points represent the smallest sinusoids that we have in the visibility equation. And this is just the familiar resolution limit. We can't resolve structure smaller than that. And so this is like a single dish radio telescope or an optical telescope. You get higher resolution when you have a bigger telescope, but of course it's a finite resolution. So unlike a single dish telescope, there's also an inner boundary. Here we can't get the antennas closer together, so that leaves a central hole in the UV plane. And so that means there's no information on larger scales than are sampled by the shortest baselines. So this really is different than single dish observing. Structures that are sufficiently extended on the sky won't be sampled by any sine waves, and so won't be by big enough sine waves, and so won't be visible. Then we have all these crazy gaps and irregular coverage in between the boundaries. And in general, this means that the sampling theorem is violated and some information about the sky brightness distribution is missing, and we'll have to do something about that. All right, so that was maybe a little abstract. Let's look at a visual demonstration of this. Here's again Rick Perley and his Fourier transform. Now, if I restrict the sampling of his Fourier transform by throwing away all the values at large U and V, okay, then what does the Fourier transform look like? Well, it's missing all the samples of small sinusoids and fine scale structure. So it just becomes all blurry. The resolution is lower and the fine details are lost. Likewise, if I take this Fourier transform and I restrict the sampling to throw away the central part of the UV plane, right, the large sinusoids, then we get this version of Rick, which is quite different, right? But it's highlighting the small scale structure, and in particular, you can see that the letters on his shirt now are very sharp, and you can read the words very well, very large array. And so by throwing away the short baselines, the large scale structure, we've been able to highlight the small scale structure. All right, so now you have your calibrated visibilities from your observations, and you know enough about Fourier transforms. What is it that you do? So you might just stop here and analyze the visibilities directly. That is, you might not want to make an image at all. So this works really well if you know your brightness distribution is simple, like it's composed of a few point sources, or it can be described very accurately by a few parameters, maybe like a simple ring. Or if there's a purely statistical description of your visibilities, like the power spectrum is all you're interested in. And all of this can take advantage of the fact that the visibilities have very well-defined noise properties. And there's a lecture about non-imaging analysis in the school. All right, the other thing you can do is you can take these incomplete noisy samples of the visibility function and make an image. So how do you do that? Well, you take the Fourier transform of the samples you have, and it creates a distorted version of the sky brightness distribution. Then you want to somehow account for the incomplete sampling to build up a model of the sky brightness distribution, and then work with that model to do the science that you want to do. And there are several software packages that do this, and familiar ones are CASA that you'll use later in the school. There's Myriad, there's APES, there's Gildis, all have tasks that essentially take a Fourier transform of the visibilities and then treat the incomplete sampling issue. All right, so when I say imaging, what is it that I really mean? Here's a formal description of the process. So using the interferometer, we've sampled the Fourier domain at a number of discrete points. So we have a sampling function, S, that consists of a collection of delta functions. Now, we can Fourier transform the visibility function multiplied by the sampling function that we have to get our distorted view of the sky brightness that I've called here TD. If we apply the convolution theorem to this equation, then we see that the true sky brightness, right, the T of Lm that we're interested in, is convolved with the Fourier transform of the sampling function to give this distorted view of the sky brightness. And this Fourier transform of the sampling pattern, this little s, is often called the point spread function, or for radio interferometry, the synthesized beam. And this is what all those orange pictures represented in the example that I showed you a few minutes ago from actual SMA sampling. That is, I showed the Fourier transform of the sampling function. And you could see how it changed as we added more antennas and more samples and let the Earth rotate. So in radio astronomy jargon, this distorted sky brightness is often called the dirty image, which is the true image convolved with the dirty beam. And the word dirty comes from the fact that we'll use a clean algorithm later to fix up the incomplete sampling. So here's a look at this graphically. All right, so just for the purposes of an example, here's a sky brightness distribution that I made up, which looks a little bit like a protoplanetary disk at the center, along with a compact blob in the upper right that has a quarter of the flux of the disk. Okay, so here's our sampling function again. And we take the Fourier transform of the sampling function, and all of its incomplete sampling and whatnot gives us this point spread function, this little s, which is the dirty beam. Now, if I convolve the dirty beam with what I know the sky brightness is, because this is a model sky brightness that I'm interested in, then I get something that looks like the following. This is our distorted view of the actual sky brightness. Now, I know that the sky looks like the panel in the lower right, but because my sampling with the SMA was so bad, I end up with the panel here on the lower left. But I am also pretty happy because we finally got to the point of actually making an image from our data. Okay, so next I'm going to go through a few practical considerations, and then we'll talk about what we do with this dirty image. So one practical issue is the field of view. So the antenna response is not uniform across the whole sky. You've heard about the antennas, and the response is generally characterized by a primary beam that has a full width half max response that's approximately the number of wavelengths across the antenna diameter. So in general, the response that's well beyond this primary beam isn't important for SMA observations. So this antenna response function modifies the sky brightness distribution. That is, the true sky brightness is changed by the fact that the antenna is not uniformly sensitive across the whole sky, but it's just a simple multiplication. And the primary beam attenuates the sky brightness far from the center of the field. So you can correct for this with a simple division by the response pattern in the image plane. So this is usually called a primary beam correction. Now, if you need to observe a larger field of view, then you need to point the array at more places in the sky, and this is called mosaicing. Here's our sky brightness of Rick Perley again. If you observe him with the SMA, the 6-meter antennas at 345 gigahertz, then you're good with a single pointing of the array. Rick fits comfortably inside. But suppose you wanted to observe Rick with ALMA at a higher frequency at 690 gigahertz, then you're going to need a lot of pointings, many primary beams, in order to cover the area subtended by Rick on the sky, and you'll need to make a mosaic. Okay. So I said many times, well, you take a Fourier transform. What does that mean? Well, in fact, you could just calculate the double integral in the basic equation by multiplying by lots of sines and cosines and summing, but it's a lot of computation. It blows up very quickly as you increase the number of visibilities. In fact, it can be done by brute force for a modest number of visibilities, but it's generally not practical for most modern imaging applications. So it turns out that there is an alternative, and this is called the fast Fourier transform algorithm, or FFT. And it's much faster, much faster than the simple summing to compute the integral. However, as Rick Perley says, this speed doesn't come for free. The FFT algorithm requires that the data are sampled on a regular grid. And as we've seen from our UV coverage plots, radio interferometry does not generally provide samples of the visibility function on a regular grid. So that's an issue. Another issue is that the FFT is periodic, so you might also have to worry about aliasing, but that's something that I won't go into in any more detail now. So how do we deal with the FFT? Well, there's a process in imaging which is called gridding, which is used to resample our measured visibilities onto a regular grid to be ready for the FFT. So this kind of sounds like a bad thing to do, but it's not so bad. The conventional approach is to use a convolution with functions that have special properties. Now, a convolution, well, it turns out the visibilities are already a convolution, right? If you remember that the sky brightness is modified by the primary beam, what that means is that the visibilities are convolved with the Fourier transform of the primary beam already, right? That's the convolution theorem. So if the width of the convolution function that you use for gridding is small compared to that, then the impact is negligible. So the cell size that matters in the UV plane turns out to be something like half the dish diameter. So mathematically, the measured visibilities multiplied by the sampling function are now convolved with this gridding function g of uv. And when we do the Fourier transform of the gridded visibilities, we get the dirty image multiplied by the Fourier transform of the gridding function. And we'll have to take that out of the image and also out of the beam. Of course, the software packages do all this for you. You might be interested to know that the common gridding functions are these so-called prolate spheroidal functions, which you might Google or read about on Wikipedia. They're compact in the UV plane, so they don't do much damage. But in the image plane, they also drop to 0 quite quickly at the edge. So these are kind of cool special functions that work well for this purpose. There are also a lot of other things that can happen in the gridding stage. Other gridding steps include applying functions that will apply primary beam weighting and offsets for mosaicing, can apply functions that apply wide field phase shifts, this so-called W projection. You can use functions that correct for the primary beam differences among antennas in A projection, and there are others. All right, so that's gridding. What about the image size and the pixel size? So when you make an image, how big should it be? So making this kind of image is not like taking a picture with your cell phone, right? Your cell phone has a little chip in it that has some number of pixels that detect the light, and that's the size you get. So what happens with radio interferometry when you take your FFT? Well, the natural choice is often the full field of view, which is determined by the primary beam of the array antenna. So for the SMA at 870 microns at 345 gigahertz, the full width half max is 35 arc seconds. So you might make an image that's twice that size. In the rare case that you have strong sources beyond that and the array has some sensitivity to them in the antenna side lobes, then you may have to worry about that because the FFT will fold that in, will alias them in. So you can make a larger image, which just includes those sources, or you can subtract those sources from the visibilities somehow, or something else. But that's an unusual situation. Okay, what about the pixel size? So unlike your cell phone, right, there's no physical element that determines this. What you really need to do is satisfy the sampling theorem to make sure that the pixels are small enough to represent the details that you measured with your longest baselines. So you need 2 pixels to sample the angular scale that corresponds to the longest baselines. In practice, it's actually good to have more than 2 because it helps with deconvolution that we'll discuss later. So maybe 3 to 5 pixels. So for the SMA, again, at 870 microns, 245 gigahertz with 500 meter baselines, that's a pixel size that's something less than a tenth of an arc second. Okay. There's another aspect in the visibility gridding process that we can adjust that's very important, and that's the visibility weights. So there are different so-called visibility weighting schemes. Now, the visibilities come with a weight that's based on the noise of the measurement, but we're not restricted to that. You can always, remember, you can always change the angular response of the interferometer by adding more samples, right? If you want higher resolution, you can add longer baselines. If you want better sensitivity to larger scales, then you can add shorter baselines. But all of that would require more observing. Another way to change the angular response is by introducing a weighting function into the gridding process that modifies the sampling function. So this is another function, W, that multiplies the sampling function, and it's something that we have complete control over. It also changes the dirty beam shape, because remember, the dirty beam shape is the Fourier transform of the sampling function. And we're effectively changing the sampling function with this weighting function. And these weighting functions are typically used to bring out features on different angular scales from the same data sets. So what are the common weighting schemes? The software packages, again, give you a number of options, and we'll go through the three most common ones now. Okay, one option is called natural weighting. So natural weighting is just using the variance of the visibility, that is 1 over noise squared, which comes with the measurement. This noise is generally what's measured and delivered with the visibilities. So why would you do this? Well, the advantages are that each visibility is weighted by its variance. And so this gives you the image with the very best sensitivity, or the best sensitivity to point sources that you can make. Because you have visibilities on different baselines, and so you have to specify what you want to be sensitive to when you make a statement like that. It gives the lowest RMS noise level in the image. So why wouldn't you want to do it? Well, one reason is that with Earth rotation synthesis, you usually end up with more short baselines than long baselines. That is, there's a higher density of points near the origin of the UV plane than far out. So this weighting tends to emphasize the shorter baselines, assuming that the noise is roughly equal on all baselines. And shorter baselines, right, means lower angular resolution. It's also true that usually there are many sample density variations in the UV plane, so natural weighting tends to give a lot of structure to the dirty beam. So this image here on the right is the Fourier transform of the sampling pattern that I showed you earlier from the SMA example, and it used natural weighting. I'll just note, if you fit a 2D Gaussian to the central core of this image, the size is 0.59 by 0.50 arcseconds. We'll use that for comparison in a moment. So the other extreme of weighting functions is so-called uniform weighting. So uniform weighting is a function that's inversely proportional to the local density of samples. That is, if you have measurements in a cell in the UV plane, then it has a weight, and that weight is a constant. Otherwise, if you don't have measurements, you have a weight of 0. So these weights are not related to the visibility noise directly. So the advantage to this scheme is that the UV plane is filled more uniformly. That means there's generally less structure to the dirty beam pattern. It just looks better. And this image here is the uniform weight dirty beam for the exact same UV coverage from the example that I showed you earlier. Now, uniform weight provides more weight to the longer baselines, because the weighting doesn't care that there are more visibilities closer to the center of the UV plane. And the result is that the angular resolution is higher. So that's good. What's bad is that we're downweighting a lot of data. All of that data at shorter baselines doesn't count as much because we're not using each visibility the same way. So the noise is higher. So you get higher resolution with uniform weighting, but it tends to be noisier. Another disadvantage of uniform weighting is that sometimes you can get into trouble if you have very sparse UV coverage with just a few occupied cells, which end up having the same weight as cells that have a lot of samples. So this can be a bit messy in the Fourier transform. And in this case, if you fit a 2D Gaussian to the core of the dirty beam here, it's 0.35 by 0.30. It's almost twice as narrow as with the natural weighting. So that's good if you want higher resolution, but it's going to cost you with higher noise. Now, in the old days, that's all there was, natural weighting and uniform weighting. And then in the 1990s, a smart graduate student named Dan Briggs came along, and he invented what's usually called robust weighting. So this is a variant of uniform weighting that avoids giving too much weight to cells that would have high natural weight. Each of the software packages implements this robust weighting somewhat differently, which is a little confusing. I think the easiest way to think about it is this way, with a threshold parameter. So the weighting function here is 1 over the square root of 1 plus the natural weight squared over the threshold squared. So if you choose a high threshold, then this looks a lot like uniform weight. And if you put in a low threshold, then you get something back that's close to natural weight. So in essence, you have an adjustable knob that lets you go back and forth between natural weight and uniform weight. So you can go back and forth between the best point source sensitivity and the highest angular resolution. So you might be wondering, well, so what? Well, the remarkable thing that Dan Bregg showed was that you could get most of the sensitivity of natural weighting and most of the angular resolution of uniform weighting at the same time. It's not intuitive that that should be true, but it is, and it's awesome. So in our example, if you tune that parameter to the middle of its range, you get this dirty beam that I'm showing here. So it looks a lot like the uniform beam, and the 2D Gaussian fit to the core shows that it has most of the resolution of uniform weight. And as I'll show in a minute, it has most of the sensitivity too. So there's one more adjustment that people often make, which is called tapering. So what tapering does is it multiplies the visibilities by a Gaussian function in the UV plane. And there's an adjustable parameter that defines the width of the Gaussian. So remember, by the convolution theorem, this is like convolving the image by a Gaussian. So in this example here, I've just applied a taper to make the core of the dirty beam bigger, 1.5 arc seconds. So why would you want to do that? Well, this gives less weight to long baselines, so you get lower resolution. And that can improve your sensitivity to extended structure. The disadvantage, of course, is now we've downweighted some data, so the noise per beam is higher. And there are limits to this usefulness because as you downweight more and more data, you have less and less sensitivity. You have higher noise. So if you really want better sensitivity to larger scales, then what you should do is get data shorter baselines. But in the absence of that, you can try some tapering and see if it helps. All right, so here's a quick recap of the visibility weighting schemes and the noise. So remember, natural weight gives equal weight to all visibilities by their noise, so it gives the lowest RMS noise level in the image. Uniform weight gives equal weight to filled UV cells, so you get higher resolution but higher noise. Robust weight is a continuous variation between the natural and uniform weight. And tapering downweights long baselines to give lower resolution, but improved brightness sensitivity. So here are these dirty beams from the example again. In this case, natural weighting gave a fiducial noise of 1 millijansky per beam. You can see the uniform weighting, the noise is more than twice as high. The robust equals 0 weighting has, again, most of the resolution and nearly all of the sensitivity that you could get from either one. And of course, you can combine a taper with any other weighting. So here's an example where I've tapered the natural weight and gotten a bigger beam. And here's an example where I've tapered the robust equals 0 to get a beam size which is the same as the natural weight beam. It has a little bit higher noise, 20% higher noise, but it has a different beam shape, a different structure to the point spread function, which may be useful. So the same resolution, but a somewhat different point spread function. So to summarize all of this, the imaging parameters provide a lot of freedom, and the appropriate choice depends to some extent on the science goal. You might want lower or higher resolution, right, from the same data set. Or you might want the best point source sensitivity or not. Or you might want better or worse side lobe structure on your dirty beam, depending on how complicated your image is. And you might want to apply a taper to improve the sensitivity to large scales or reduce the side lobe structure or match resolution from a different data set or something else. So when you make an image, but there are a lot of different images you can make. And that's one of the great things about imaging in interferometry. All right, so far, we've only made this dirty image, and it's hard to do science on an image like that. So what do we do about that? Well, we have to get beyond it somehow. Before we discuss that, let me just put something in your minds that will keep you up at night, okay? You have to realize that because there are parts of the Fourier plane that you haven't sampled, right? There isn't just an image. There is an infinite number of images that are compatible with the visibilities that you've measured. That is, there are holes, right, in this UV coverage in the Fourier plane. So there's information that is missing. And there's also noise, and that makes the situation even worse. So what do we do? What we do is we do deconvolution. And the basic idea here is that we use some nonlinear technique which we'll use to interpolate or extrapolate the visibilities that we've sampled to fill in the regions of the UV plane that we haven't sampled in order to make a plausible model of the sky brightness distribution. And there's no unique prescription for that. The answer actually depends to some extent on what you mean by plausible. And this requires some assumptions about what the sky brightness is like in the unsampled regions, of its Fourier transform. One key assumption for all the deconvolution algorithms in radio astronomy is that, of course, the real sky doesn't look like the dirty beam with all those crazy symmetric spokes and negative regions and the like. Okay, so let's talk a little bit more about deconvolution in radio astronomy. The two most common deconvolution algorithms in radio astronomy are called clean and maximum entropy. So for clean, the a priori assumption about the brightness distribution is that it can be represented by a collection of point sources. And there are many variants that have been developed for various purposes, but all basically go back to this same a priori assumption. For maximum entropy, which is a special case of forward modeling that minimizes an objective function that includes the data and a regularization term, the a priori assumption is that the brightness distribution is both smooth and positive. So being smooth is sort of the opposite of being a collection of point sources. So this is kind of another extreme in the assumptions of deconvolution. And there's also a vast literature about the meaning of entropy in a Bayesian sense, which is fascinating to read. And these two most common deconvolution algorithms are readily available in the common software packages. But I would like to stress that deconvolution is a very active research area, and new methods are appearing all the time. And the Event Horizon Telescope M87 imaging paper brings in a few new ones and discusses their justifications, and is really is worth a read. Okay. Since most of the time people use clean, we're going to go through clean in some more detail. All right. This is what you're going to use on your SMA data as well. So the original version of clean from Hogbaum is purely image-based, and it goes as follows. So the first thing you do is you make the dirty image and the dirty beam. And usually you make the dirty beam twice the size of the dirty image. And you go locate the peak in the dirty image, that is the highest amplitude point in the dirty image. And then you subtract a scaled version of the dirty beam at that position, where the scaling is given by a loop gain parameter. It's a fraction, and it's typically like 0.1. So you subtract 0.1 of the dirty beam, and you get a residual image. Now, you add that peak, that subtracted peak to a model, and that's known as a clean component. So it's a delta function. It's a location and an amplitude. Then you look at the residual image, and if you haven't reached a stopping criterion, then you go back to step one, you find the next highest peak in the dirty image, and you continue. So in the end, you've decomposed your image into a list of point sources with their location and amplitude. And you have probably nothing left in your residual image. So there are variants on this that do the same work better and more efficiently. So one is the Clark clean, which instead of using the whole dirty beam, uses a small patch of the dirty beam. And it subtracts your clean components from the gridded visibilities all at once using an FFT. And a related algorithm, which is the heart typically of T-clean that people use, is Cotton-Schwab clean, which subtracts the clean components from the ungridded visibilities, which is a more accurate thing to do. But then you have to repeat the entire imaging process to create the residuals. Anyway, those are details at some level. The question you might be asking is, well, how do you know when to stop cleaning? So usually it's when the last peak in your residual image is small relative to the noise, because you don't want to be making point sources out of the noise. So one stopping criterion is to say when the peak is less than, say, twice the RMS noise level in the residual, then it's time to quit. Another stopping criterion that sometimes used is to clean down to a fraction of the dirty beam maximum, say 1% of the maximum. So this is handy when the image has such strong sources that you'll never reach a noise threshold, that there are systematics that prevent you from ever reaching a noise threshold. And yet another stopping criterion is to just pick an arbitrary number of clean components, like 1,000, which has no justification at all, but people do it sometimes. Okay, what about this loop gain parameter? How much of the dirty beam do you subtract at each iteration? So values of something like 0.1 to 0.3 typically give good results. The default in the software is usually 0.1. If you have an image that consists of point sources, then you might turn that up to a larger value, 0.3 or 0.5 even, which will make the clean go faster and represent the image very well. If you have an image that's smooth, however, sometimes using lower values can help. You can turn the loop gain down to 0.05 or 0.03. Then you decompose the smooth emission into lots of little point sources, and it might represent the structure better, but it also will take longer. And then there's an issue called finite support. So you can include information that tells the clean algorithm where to search for point sources, that is, where to find its clean components. If you know that the emission is confined to a particular region, maybe from a lower resolution image, then there's no need to look outside that region for a signal. And these constraints are usually called clean masks or clean boxes. And this is useful, sometimes essential, to get the best results with clean. But it can also be dangerous because you're adding information. And creating masks can be a very tedious manual process, although new automatic algorithms like the one in CASA actually work reasonably well. So the last step in clean, after you've gotten your list of clean components, is to create a so-called final restored image. So how do we do that? We make an image with all the point source clean components, and then you convolve the point source model with a so-called clean beam. So this is an elliptical Gaussian fit to the central peak of the dirty beam. And then you add back the residual dirty beam that's, the residual dirty image that's mainly noise. And then your restored image is your best estimate of the true sky brightness. And the units of the restored image are mostly Janskys per clean beam area. I say mostly because your clean component model, when it's convolved with your Gaussian, is Janskys per clean beam in terms of units, but the residuals are not. And the fact that those units are mismatched is something that can create a problem, and one can correct for that. People have known for 25 years how to correct for that. It's just not usually done. Finally, I'll mention that there's an amazing paper by Schwartz in 1978 that proves that this clean algorithm is statistically equivalent to a least squares fit of sinusoids in the case of no noise. Of course, there always is noise, but this paper gives some theoretical foundation for using the algorithm. All right, if you didn't completely follow that recipe for clean, I'm going to go through a graphical example of how this clean algorithm works. And hopefully it'll become clear. Okay. So on the left here, we have the dirty image from natural weighting. And we start, right, with no clean components and a residual image that's equal to the dirty image. That's how we start. Now, we want to find the highest peak in the dirty image and subtract a fraction of the dirty beam and repeat that process. So here's the clean components and residual map after 30 iterations of this. Okay. So you can see this cluster of point sources in the center and one in the upper right that are starting to represent the emission in the image. And the residual map now has quite a bit less total emission than the original dirty image. So here's 100 clean components. Now you can see there's even less in the residual map. Here's 300 clean components, and you can see there's even less. And here's 585 clean components. So why 585? Well, that's where the algorithm stopped when I set the threshold for the residual map of 3 times the RMS noise level. So this central panel of point sources of clean components is our model of the sky. It's not a great looking model, but that's what it is. Now here's the restored image, okay? So if I convolve the model with an elliptical Gaussian, which is fit to the central part of the dirty beam, and I add back the residuals, this is the result. So it looks a lot like a blurry version of the original sky brightness model. And it's conventional to put an ellipse in one corner of the image to show the full width half max of the so-called restoring beam, that Gaussian we convolved by, which represents, and to some extent, the resolution of the image. And now you can go ahead and do your science on this image. So the final image that you make depends on the imaging parameters. It depends on the pixel size, the gridding function, the visibility weighting scheme, and all these other things that we talked about. And then it also depends on the deconvolution algorithm you use. And for clean, what parameters, how many iterations, what stopping criterion, etc. So here are the final restored images for the different weighting schemes from clean that we've discussed. So the first is the natural weight image, which is what I just showed you. And the second is the uniform weight image. So you can see it has higher angular resolution. You can see that central gap in the disk in the center better. But it has higher noise. And this robust equals 0 image, the third panel, has most of the resolution and most of the sensitivity of the first two. So it's a nice compromise. And on the right, here's a tapered image to see if there's any more extended emission that was hard to see in the higher resolution images. And there isn't. We know that by construction of the model. But it's even lower resolution, blurrier look at the data. Okay, so clean's been extended to work better on smooth emission with so-called scale-sensitive methods. The standard clean algorithm doesn't work all that well on smooth extended emission, where you need a lot of point sources to represent it. It's just, point sources aren't smooth. But we can take advantage of the fact that adjacent pixels are not always independent. In a trivial sense, we've oversampled the point spread function with 3 to 5 pixels, and so they're already not independent at that level. But if you have an extended structure that covers many pixels, say 1,000, it might be characterized better by fewer parameters than 1,000 individual pixels. For example, if it were a Gaussian, then you'd need just 6 parameters to describe it all. And so what scale-sensitive deconvolution algorithms do is they employ fewer degrees of freedom in their solutions to model plausible sky brightness distributions. And a common example is multi-scale clean. This makes a collection of dirty images at different resolutions by convolving with a set of input scales. And then the algorithm finds peaks across all the scales and iterates like standard clean. So that's one approach to dealing with extended emission with clean. All right, what about the maximum entry algorithm? So this is cool. Here you want to find the least biased image that agrees with the visibility samples that you have. And you do this by minimizing a function that contains a so-called entropy term and a data term. And the entropy term in this case is this sort of t log t function that requires positivity because of the log. And this alpha in the minimization is a Lagrange multiplier, and the chi-squared is some measure of agreement with the data. It's just the classic sum of visibilities minus their Fourier transforms divided by the noise squared. And then in this maximum entry algorithm, there's also this quantity m, which is the default image that I'll return to in a moment. So it turns out there are ways to solve this kind of equation reasonably quickly. There's a fast solver that was introduced by Tim Cornwell a number of years ago, and even that's been improved on since. Okay, so what about the maximum entropy algorithm? In the absence of any information in the visibilities at all, the maximum entropy algorithm returns the default image. So if you don't know anything, then you typically just make the default image flat, uniform. But if you do know something, say from a lower resolution image, then you can use that. Another thing is that, like a single dish image. Another thing that's neat about maximum entropy is that you can generalize this chi-squared minimization to combine different kinds of observations, say observations from different telescopes. You don't have to use this maximum entropy. There are other measures of entropy. One that's available in some of the software packages is replacing that log with a Cauchy function. So then it doesn't require positivity anymore. Sometimes this is called maximum emptiness. This is a relatively fast algorithm for very large images. The famous VLA image of Cygnus A that was in the introductory lecture to this school is a maximum entropy image, for example. An interesting aspect of maximum entropy is it doesn't use any direct information about the dirty beam shape in doing the minimization of the objective function. So, it can be bad in the sense that if the dirty beam has a lot of structure, then maximum entropy can have a hard time because it it starts to believe that the side lobes of the dirty beam might be real features because it doesn't know what the dirty beam doesn't really use the dirty beam shape. All right, another property of maximum entropy images is that the effective angular resolution in the image is signal to noise dependent. So if you have a component that has high signal to noise, you'll be able to resolve it as well as the longest baselines in your image. And I'll just say at the end here that my experience for the SMA is that maximum entropy is often more difficult to drive than clean. It doesn't work as well, but it's still really fun to play with. So here's our example with a maximum entropy result that I got just from blindly running the task. And you can see the maximum entropy model came out pretty well. And you can make a restored image in the same way with a maximum entropy model by convolving with a restoring beam and adding back the residuals. And here's the restored maximum entropy image that one can use to do science. So, okay, that's it for deconvolution. And we have just a few more topics to discuss. Here's a little bit of jargon that's useful to know about so-called image quality measures. So one term you'll hear a lot is dynamic range. Dynamic range is just the ratio of the peak brightness in an image compared to the RMS noise level in some part of the image that's empty. So this is an easy way to calculate a lower limit to the error in the brightness in a non-empty region. So in this example, the peak is 88 millijanskys and the RMS is 1 millijansky per beam. So the dynamic range is just 88. Another term is fidelity, image fidelity. This isn't used as much because it's defined as the difference between a reconstructed image and the true image, or the correct image. So to determine this, you need to know what the correct image is, and you generally don't know that. But if you start with a model, like we did here, you can measure it. So you can check how good the fidelity of an image is for a particular model and a particular sampling pattern in the UV plane. Since it's the input model over the difference, it's just the inverse of the relative error. And the reason that I mentioned fidelity is because dynamic range can be misleading. You might have a very high dynamic range, but the fidelity might actually not be that good. That is, the dynamic range might be 88, as in this example, but the fidelity on the disk, say in the center here, might be a lot lower, like 15 or 20. In general, you should just be wary that the reconstruction of the image where you have signal is often not as good as you might think from the regions of the image where you don't have signal. And that's captured in the dynamic range, but it's not the same as the fidelity. Okay. Next, I want to make a comment about large-scale structure, in particular, invisible large-scale structure. This is an insidious problem that you should always think about when doing interferometry. So inevitably, there's a central hole in your coverage of the UV plane because your antennas can only get so close together, so there's a gap in the center. And what this means is that extended structure may be missed entirely or attenuated or even distorted. So this may be a problem, but how do you know if it's a problem? So I'll just say in general, you should estimate if this so-called lack of short baselines will be a problem. And the very best way to do this is to simulate observations using a model of the source emission. Or short of that, you can at least check some simple expressions for Gaussians or disks of particular sizes. So here's your homework problem. The question here is, By what factor is the central brightness reduced as a function of source size due to missing short spacings for a Gaussian, with a particular size? So I'll tell you the answer. You can look it up in the reference below. The central brightness is reduced by 50%, as shown by this equation. And all I'll say about this is it's way more than you might imagine. In the ALMA literature, there's, or in the proposer's guide, there's talk of a so-called maximum recoverable scale. But that scale is not what you might think. One recovers something like 5% of a uniform disk of that size scale. So you recover some flux from the maximum recoverable scale, but not very much. So this can be a little bit misleading. And it really is useful to check on this. Okay, so here's an example. I think a picture's worth a lot of words here. So here's our original sky brightness model in the upper left, and here's a new model below it. And in this new model, I've added an extended blob that has 10 times the flux of the disk. Okay, so it totally dominates the model. Now here are the natural weight images with the UV coverage that we had. And this imaging isn't great, but it gets most of the blob back. But if I don't have any short baselines, if I cut out all the baselines shorter than 75,000 wavelengths, so roughly the compact configuration, right? Then, well, lo and behold, right? It's like it was never there. And it's the most important thing in the image, and you don't see it at all. So please be careful with missing short spacings. All right. Finally, I'll just make a few comments about spectral lines and polarization. All of the discussion so far in this lecture has really just applied to a single channel in some sense. And the science may require many channels, right, across some bandwidth. So examples include emission or absorption from spectral lines from atoms and molecules. Here's an example of Keplerian rotation of a protoplanetary disk from the SMA in carbon monoxide across a series of frequency channels, of radial velocity. There are other examples. You might have a significant continuum spectral slope or curvature that you want to measure across cross frequency or wavelength. And from a technical perspective, having many channels can be very useful. You can edit out interference spikes that only affect a very narrow frequency range. And you can avoid bandwidth smearing. So this is the issue that if you have a broad band, then what UV point does it actually correspond to? And if it's broad enough, then you get some smearing in the image plane that results from averaging over the frequency band. And this can also limit the useful field of view. So the bottom line is you just treat each channel separately, and you do all the imaging and all the deconvolution for each channel separately. That's how you deal with spectral lines. And the same is true of polarization. You can measure all four Stokes parameters, I, Q, U, and V, and after proper calibration, they're independent of each other, and then you do the imaging and deconvolution for each Stokes parameter separately, and then you can combine those images to make quantities of interest like fractional linear polarization or something like that. Okay, so a few concluding remarks. What should you remember from this talk? Well, interferometry samples Fourier components of the sky brightness. And you make an image by Fourier transforming the sampled visibilities. And deconvolution attempts to correct for the inevitable incomplete sampling that you have. So remember that there are an infinite number of images compatible with your visibilities. Missing or corrupted visibilities affect the entire image. And as an astronomer, you see you have to make some decisions in imaging and deconvolution. But it's all fun and worth the trouble because in the end you get high resolution images. So there are many, many issues that I didn't cover in this talk, but please look at the references for answers and we can talk about others in the discussion section. Thank you.